Question 3 from the 2010 electricity paper for Level 2 Physics. Electric motors and generators, submarines, operate underwater where there is no air, in case you didn't know that. Most submarines have diesel-electric engines. The diesel engine operates normally when the submarine is near the surface, but it doesn't drive the submarine's propellers directly. Instead, it powers an electricity generator that charges up huge batteries. These spin an electric motor that turns the propellers. Once the diesel engine has fully charged the batteries, the submarine can switch off its engine and go underwater, where it relies entirely on battery power. So there is a motor as well as a generator in a submarine. Now, regardless of the reasons why that is, it's probably because diesel fumes need to be evacuated into the air through the exhaust. When you don't have a lot of air to evacuate diesel fumes into underwater, and it probably doesn't work well going into water itself because it would, the water has a higher pressure and would flood the motor. Anyway, there's a motor as well as a generator. Give one different example of where a generator is used other than in a submarine. Okay, this could be anything. Okay, anything where you're using mechanical rotational energy to charge a battery or produce power. So, for instance, you might have in a car to charge the battery. Charger. You could have on a bike a dynamo to make the light go on the bike as well. Give one different example of where a motor, so there's a motor, not a generator, is used other than in a submarine. Okay, this is an electric motor. So if you say, straight after I've said car battery charged using an alternator or a generator, which is alternator's type of generator, if you then say in a car, when you're talking about the engine, unless it's an electric vehicle, you'd be wrong. So let's write electric car. But you would also use it for window winders in electric car, electric window winders. Look, there are just so many here that you could possibly have. It's, yeah, so many. Fans are a big one. Anyway, moving on. 3, because this is another long question. Discuss the difference between a DC motor and a generator in terms of, we've got two things to discuss the difference between a DC motor and generator: the principle underlying its working and the energy conversion. Okay, so the energy conversion is probably an easier place to start because for a motor you're taking electrical energy and you're converting that into kinetic rotational energy. Whereas a generator is doing the exact opposite. It's taking kinetic or movement energy, rotational, and it's converting it into electric potential or electric energy. It doesn't have to be electric potential. Usually it's electric potential though. So if we go up to the principles underlying it, you've got two right-hand rules you've got the right-hand slap rule to deal with for motor, and you've got a rule for generator as well, but you operate them slightly differently. But the principle underlying its working is that for a motor, current flow in magnetic field produces a force, and that force is used to make something turn. That's kind of the whole point. And that's for a motor. For a generator, you're using a force to push a wire through a B field, magnetic field, and that motion drives or applies a force to the charges in the wire. So force on the charges, Q, in the wire, which cause current to flow, and you can take that current and light things up, or you can charge batteries or do whatever you're doing. What else? It's always good to mention when you're talking about the principles things like keywords such as, you do definitely have to mention magnetic field or electromagnetic induction and induced voltage and all that kind of stuff. So that's the main idea. Generator induces a voltage when you move a conductor through magnetic field, and a motor induces a force when you run a current through a wire in a magnetic field, or a conductor in a magnetic field. Anyway, moving on, the diagram below is a simplified electric motor. It doesn't look very simple to me, it looks a little bit complex, but if you've never seen them before, then it would. But if you have seen them before, study them, you'll know what's going on. So we've got the north side of the magnet, south side of the magnet, the coil on the inside, there's part of it missing. You would probably see the rest of it appear something like that, and that part's going to rotate. That's why there's a slight curvature to the magnet surfaces there. And the commutator here in the carbon brush makes up a thing that rotates while the brushes are attached to the circuit. So the brushes stay in place, and as the commutator moves, depending how you arrange this, you could have the brushes on the inside moving while the commutator stays fixed. And it looks like there's a split ring commutator with a gap in the middle at the top and bottom. A little bit hard to see, but that gap ensures the change in direction of the current about the coil as it as it completes its rotation, and that change occurs right at the top and at the bottom. So when the coil is vertically oriented rather than horizontal as it currently is, and that allows the force to maintain the same rotation, same direction of rotation on that coil. Anyway, you should know that, but that's just an overview. So we've been given the length of the coil, AB, so that's one side. Okay, we've got the strength of the magnetic field, we've got the voltage across the terminals of the battery, and the total resistance of the wires. So that's going to help us to calculate the current, which we won't jump ahead of ourselves too much, but that's going to be part of it. B, calculate the size of the magnetic force on AB, which has 100 turns of wire. The size of the magnetic force on AB. That's just a little bit confusing. I think it's saying, because normally when you're talking about the size of the magnetic force, you talk about the size of the magnetic force on the entire coil. And that's just a little bit hard to work out if you're told to deal with AB, because there's actually twice that length on both sides. And normally that's what I'd assume they're doing. I'm actually going to have to look at the marking schedule to find out for certain. So it's a bit of a fault with the exam. It could be confusing. Because normally, because there's two lengths of AB, or there's this other, we might call it CD, as D's already been used, CE. So if we're trying to find the total force, we'd have to take twice the length of AB, then times it by the 100 turns of wire. And I'll just have to look in the marking schedule to see whether they do that. Okay, so the marking schedule doesn't worry about twice the length, so it's just being a little bit awkward, which is a bit unkind to poor students struggling with their exams when they're doing these. But in any case, we're after the force, as we said, the magnetic force. Force is due to the magnetic field strength times the current in the wire times the length of the wire. So B, we were given, was 0.75 Tesla, and times the current. We don't know the current, but I equals V over R, so it's the 12 volts over the 4.5, that'll give us the current flowing in the coil. And then the length is 12 centimeters, which is 0.12 meters. Okay, now to get that up to 100 times, we have to multiply it by 100, because that was only for one. And when you multiply all that out, you will end up with 24 newtons. Okay, moving on. C, explain why the part of the wire labelled AD, which is 5 centimeters long, will not experience a magnetic force while at the position in the diagram. So let's just highlight that with red so you can see AD, here it is, and it's running parallel to the magnetic field, which is why there will be no force. So it's parallel, AD is parallel, there's parallel lines to the magnetic field, and it has to cut the magnetic field for it to produce a force. So AD running parallel to the field needs to cut or be perpendicular to B field. Well, it doesn't. No, perpendicular is not correct either. It has to actually cut, because you can be magnetic field can run this way, and you can be perpendicular but not cutting. You have to sort of go into the page, which is what the if you imagine the lines going out of the page like that, you'd have to have a wire moving all the way down through for it to be properly cutting. If it's moving a piece like that up and down, it's not going to, but if you moved a piece like that side to side, that would also be cutting. But AD doesn't cut the field, which is the main thing. It's parallel to. D. State 2 changes that can be made in order to make the coil spin faster. A number of things you could do. You could increase the current in the coil, which would be done by increasing the voltage. You could increase the number of turns, and you could also, I suppose, you would assume certain things are fixed, but if you could increase the magnetic field, use a stronger magnet as well. Okay.